All right, hello everybody. Welcome to my talk. Title of the talk is The New Old Supply Chain Security with Sigstore and Kubernetes this time. I want to quickly introduce myself. My name is Delitor. By day I work in IT security, and by night I work for a prototype fun project called SEC. It's about signed containers, and if you guess it or not, we try to ease the usage of container signatures. So let's go quickly about the agenda. I will start with package management as an approach to complexity. There I will quickly go over the evolution of packaging and what they do to actually reduce complexity. Then I will talk about trust, what it is and how it relates to security. And then we will finally talk about Sigstore. And here I will explain to you how Sigstore reduces necessary trust through their infrastructure, how their signing and verification process works, and two different ways to integrate it into Kubernetes. All right, packaging as complexity reduction, or a short and very simplified tale of tackling complexity and by packaging and distributing software, aka supply chains. Okay, has anybody of you heard about the term the software crisis? Okay, I guess not. It's a term that was introduced in 1968 at the NATO Conference of Software Engineering, and it was later referenced by Dijkstra in his book The Humble Programmer, and it was a term that was supposed to describe the problem that arose due to increasing power of computers that quickly led to increased program size and complexity, and therefore a decline in quality, which meant that you had unmaintainable programs, you had many moving parts, projects were running over time, projects were running over budget, and all the likes. And yeah, you probably heard of that one. So what we can see here is that complexity is basically a problem that exists for as long as programming exists. And the only reason we are still here is because we tried to live with it. And that's what this talk is about. How do we live with complexity in our systems? All right, so packaging as tackling complexity. A long time ago, there was a time where we built our programs and deployed them all ourselves. That did cost a lot of time, it cost a lot of effort, as the people in 1968 also realized. So we tried tackling these complexities by packaging our programs. A developer or a distributor took a piece of software, put them in a special format, so they can distribute it to any machine they like. That's great, right? It's easier for me as a user, it's more work for them, but I don't care. So from this humble beginning, packaging developed to what it is today, which happened essentially in 3 stages. Distribution in the form of package management, deployment in the form of containerization, and operation in the form of cloud and container orchestration. Package managing is essentially the answer to the question, how do we package and distribute software between unknown parties? That worked to some extent. So there was a domain-specific central instance that was maintained by a small set of people. And with some crypto, we ensured that the packages that were distributed weren't tampered with, and we actually knew from whom the packages would come. You may know some of them, maybe Aptitude, Pacman, FreeBSD package, and the likes. Then containers came around, and they made packaging actually composable. So you know stuff like Docker and Podman. So from the moment on, we were suddenly able to actually compose software. Yeah, it was sure it was possible to do that before, but now we could just take an image, develop our software in it, put it on top, and release it. And that was it. And that made it super easy. So this was possible by making deployment more opinionated. We split up the packages into the actual software together with its dependencies, in state and in the configuration. Then we started defining interfaces around that we standardized. They're called container runtimes, container storage interfaces, container network interfaces, and much more. And then we additionally created infrastructure around the distribution of those packages. They're called registries. So now everybody can distribute their packages as they like. And then we went even further. Orchestration quickly followed. basically what we did is we took the approach we took with containers and used that approach on configuration and operation. Think Helm, think Terraform. So yeah, that was even more complexity. So what you may have realized that by now is that what we essentially did was we took the complexity that we had on the user side and shifted it completely to the developer and the distributor. And this, in turn, resulted in even more complexity because we needed to generalize those approaches. Now, we can discuss until kingdom come if that is actually good or not. But there was one thing that missed in this whole transitioning into modern package managing. So in modern package management, you don't really have a viable way of ensuring integrity and authenticity in your packages. What we had was we had package managers. They did that kind of well a couple of years ago, because what they did was you had a special set of maintainers. They handled the packaging, they handled the updates, they handled the distribution of the packages, and you had the PKI, which was used to sign the packages and prove they are integer and authentic. Unfortunately, with the fact that we now enable everybody to publish packages in their own registries, that approach doesn't work anymore. So this is mainly due to this reason that the approach we had with packagement doesn't scale in the newer systems. So to quickly put this together, we bought complexity reduction on the one end, but increased it on the other side. Now packages can come from anywhere due to composability. There's easily a hidden tail of possible infinite dependencies. But we have no way to ensure authenticity or integrity ourselves, at least not a widespread one. And we have no conscious entity like maintainers that we can trust to do this for us, at least in the amount of software that is out there. So now I want to talk really quick about trust. Mainly because I think there are some misconceptions about trust, and I want to introduce them so we can later have a look how Sigstore actually solves some of these problems. Defining trust, especially in the context of ID, is pretty challenging because we tend to mix the technology and the human interaction when we talk about trust. And I really want to differentiate this, and that's why I want to define trust as the belief in the integrity of a group or a person. And I especially take the technological context out of here because there's a different way, or there are some different ways, to set up a system securely. Some prominent ones are cryptography, so we can use cryptography to prove the persistence of properties. Or we can use formal proofs to show that a program is following an expected behavior. Of course, these are very central to the security of our system, but this is not trust. That is a proof. There's a mathematical concept behind it, and it's logical, and we don't need to trust anybody to actually use it for trust. So to build on top of that, I want to introduce a term I really like. It's coming from literary theory. It's called suspension of disbelief, or the willing acceptance of the impossibility in reality. So I want to use this term because every system we have and we want to secure, there comes at some point the thing where we can't actually prove security anymore. That can be because we had to prove the existence of some processes people had to do, or we have to prove that people won't make mistakes, or we have to prove that a person is not malicious. Another version could be that the verifying of the correctness would just be too expensive. And at this point, we need this basic form of trust and the acceptance of the unknowability and the unprovability. To further illustrate it, I've brought you two examples to show you how this trust versus proof spectrum works. The first one is being content moderation, and the second one is signatures. Content moderation being trust first, and signatures being proof first. Okay, so the trust first approach is where a system, in a system you have a set of people or an institution, and this institution or the people are trusted with moderation. Moderation in our context meaning that they ensure that either only trusted resources are distributed or you are able to differentiate between trusted and untrusted resources. And for this system to work, we actually have to trust in the process of the institution itself. And this is, for example, what we had with package management when we trusted the maintainers to do their job properly. And as with package management, that's also the reason why this approach doesn't really scale well. An actual real-life example for this is the Docker Hub Trusted Content that was released in May 27th, 2021. And the trusted content uses different flags on, uses different flags on images to show which images Docker deems trustworthy. I've brought you a screenshot for that. Here you can see a screenshot of the Docker Hub, where I had a search, and the result shows you that you have these little pink labels there that show you that they have a special property. The tags that exist are Docker official image, which obviously tells you that this is an image from Docker. Then there's verified publishers, where Docker tells you that they have verified that the image is actually the image that came from the developer, and they ensure that those people are proper. And the last one is sponsored OSS, which tells you that the project or the image you have there is a project that is actually supported by Docker. But now we run into this problem that we really need to trust in the processes of Docker to actually deem that trustworthy. So who tells me how Docker decides on what a verified publisher is, and how do they actually verify it? And that is the problem, and that is why we can use, or for what we can use, another approach, which is the proof-first approach, meaning signatures. So signatures is just we take an artifact, we create a signature for it, we upload the signature, and then anybody can actually get the data and verify this by themselves. There are obviously no further guarantees about the security of the image. It's just that you can say, I am in the moment of signing, from the moment of signing, the image hasn't changed, and the person who was who had the private key is the actual person who provided it. Funnily, this wasn't possible in images until 2016, because the Docker image standard had some neat little trick where the checksum of your image changed when you pulled it from a registry. This changed with the introduction of Docker image format version 1.10 in 2016. They adopted for that, and just to give you a reference, the Open Container Initiative container standard was specified in 2017. Yeah, and with that out of the way, we can actually start with Sigstore. So what is Sigstore? Sigstore is a collection of tools, standards, and processes. It's a project that was part of the Linux Foundation, or it is a Linux Foundation project, and it's purpose-built around the assurance of integrity and authenticity in the context of containers and container orchestration systems. What does purpose-built mean? In this context, it means it is specifically built to be to work with OCI-compliant registries, and it provides additional tools for the integration into container orchestration systems like Kubernetes or OpenShift. They have two little other great features. One being short-lived certificates and certificate transparency. For the uninitiated, short-lived certificates means they are usually between a couple of minutes and a couple of days long, opposed to multiple months or even years. And we do that to work around a problem that is inherent to PKI structures, which is the problem of revocation. How do you get the data around? Who was revoked? All this stuff. If you just have short-lived certificates, you don't have to care about that. You just wait and don't renew the certificate, and that's it. So the other thing they do is certificate transparency. This is a process where every certificate you create is appended to an append-only log. which is a Merkle tree. And through integrity checks, you can detect if somebody is trying to compromise your certificates. Yeah, and or at least our project, chose Sigstore also specifically due to those features they have. All right, so how does Sigstore handle actual trust? So Sigstore created its infrastructure with different components that aim to reduce the trust necessary in your system and prove as much as possible. I will quickly go over the Sigstore implementation of the infrastructure. Very important here. I will be referencing their own infrastructure, how they deployed it. It's also self-hostable, and you can exchange components. So just that you know that you can, in the wild, actually encounter different versions of it. So the components used by Sigstore are a trust root, a Fulcio signing certificate authority, and their associated transparency log. Recore, which is also a transparency log, but that's the transparency log for their signatures, and cosign as the tool that is used to actually sign and verify the signatures. So here is a little overview over the components and the actions you can actually do in the infrastructure. And I will go with you now over the components and their properties. So let's start with the trust root. The trust root holds and secures all root keys that are on the infrastructure. It also provides public key material and certificates that are needed to actually trust the Fulcio and the Recore that is used. And all infrastructure keys they use are derived from those root keys. And this is where you reduce the trust, because the only trust you have to have now is in the proper running of the trust root, and all other systems are derived from this trust. To do that, they actually use a system called TUF, which is the update framework. It's a set of protocols, and it allows you, for example, to define key-specific rules. So when a key has to be updated, stuff like that. It provides a regression model in case keys get compromised or lost. It protects against different attack models that are specific to package management. And it provides a delegation system which actually enables to do the whole deriving of keys in the infrastructure. The second component is Fulcio. Fulcio is the signing certificate authority. Very important in the context of Sigstore is usually you bind your identity over your key pair. That is not done here. Key pairs are only used very temporarily to actually do the signature. The identity that is used in the certificates is provided by an external OpenID Connect provider. Sigstore supports different formats for that. So I think right now they actually support GitHub, Microsoft, Google. Then they support tokens, which is something you can do with GitHub Actions, and they support the common platform providers like AWS, Azure, and the likes. So together with the CA, you have a transparency log, which is actually a nice, neat little way to also reduce trust in your system. Because if you make things transparent and public, nobody needs to trust you. They can just check themselves. And another little neat feature is that you move the actual burden of checking to the user and don't keep it in your infrastructure. Okay, then we have Recore. Recore is the transparency log for the signatures that are created. There's also a neat little trick here. Because we have short-lived certificates, we need to actually check when the certificate was used to create the signature and if the certificate was valid at that point. To do that, every time a signature is added to Recore, Recore will actually timestamp that and add the timestamp to the signature and append it to the log. Okay, now I want to go over the whole signing process with you and the publishing and also verification process later. So, okay, we are a developer. We have created our image, and now we want to sign it. So what does happen? At first, we go to our OpenID Connect provider, authenticate against the provider, and get a token. Then we will create a key pair locally on our machine and use the key pair, the private key specifically, to encrypt the token. That is done, so we actually have a challenge with whom we can prove to the FrOSCon signing CA that we are in possession of the private key. With those two pieces of data, we go to the CA and create a request. Now the CA will take the challenge, decrypt it with the public key. From that, it will know that we are in the possession of the private key, and then it will go to the OpenID Connect provider and check if the token is valid. If those two are the case, then it will create a certificate, but before giving it back to us, it will actually poison the certificate. That is an extension of X509 that enables you to make a certificate unusable, and will add it then to the to the transparency log, which then will return to us or to the FrOSCon a proof of inclusion, which will also be added to the certificate. And if that has been done, then we get our certificate back and we can actually sign our image. To do that, we create something called a signing event. That's actually just a little piece of data that consists of the hash of the artifact, the public key or the certificate, and the signature. And that's actually the whole signing process, at least in the default version. So now publishing. So we have our signing event. But before we can publish it to a registry, what we will do is we will publish it to the transparency log. So Raycore will create its timestamp, will append the signing event to the log, which is actually called witnessing, and then will inform us that that has been successful. And then we can use the signature and the artifact and upload it to the registry. What Sigstore does is they actually use a relative path. So they upload the image to the registry as you would usually do over the path. And then they will put the signature relative to that path into the registry as well. And that is also the reason why Sigstore is only compatible with OCI registries or OCI compliant registries, because they are the only ones that enable you to upload arbitrary artifacts to the registry and not only images. Okay, so now we can do some verification. We use the CLI again for the verification. Usually, this step I'm now talking about you can skip because of the default infrastructure, but I want to include it just because of completeness. So first of all, our CLI has to go to the trust root and get itself the public key from the Raycore and the root CA, the root certificate of the FrOSCon. And if that data is there, then it will get the artifact and the signature from the registry, will get the signature from the transparency log, then it will check the timestamp, if the certificate was valid at time of signing, and then if the signatures from the registry and from the transparency log are the same, it can be deduced that the signature is still valid, and then we only have to check the signature itself. And that was how you verify in a very quick way images that have been signed with Sigstore. So now we come into to the integration of Sigstore into Kubernetes. There are currently two ways of doing that. The first one being container runtime via the container runtime CRIO, and the second one being with admission controllers. So we will first go over the CRIO integration. For those who don't know, CRIO is an open container initiative compatible runtime, and it's currently the only runtime that actually supports Sigstore signing. That's due to the reason that CRIO uses a project called Containers. Yeah, it's a very nice name. And they have some libraries to work with registries and images, and they have the image library, which they actually use to build the runtime, and those can define policies. And with those policies, you can define requirements on the downloading of images on your machine. Very important here, the policies are configured in a configuration file on the node. So that means if you have a cluster with multiple worker nodes, you actually need to define it on all worker nodes to be able to use them anywhere. Okay, the policy, with the policy you can define two things. The first thing is the scope, so just which registries are to be checked. If you want to check a registry, do you want to check only namespaces or a specific image? And then you can define what kind of signing system you want to use and what formats for that. For that, I have brought you a little example. First, we define transports. Transports are just the modus on which, with which the image is to be acquired. In our case, this is Docker. So that means that the registry we are talking to has to be compliant to the Docker registry standard. Then we actually give the registry plus path. In this case, we want to apply only the policy only to a single image. And then we just give the information that is needed to actually check the image. So in our case, we say we want to have a Sigstore signed image to be checked, or we want to check for a signature from Sigstore. Then we have to give the full queue information. In our case, that's the path of the certificate, which OIDC was the issuer of the token, and the subject that is part of the certificate. And we have to give the public key path from the record. And that's actually it from a container runtime point of view. Yeah, and now we can talk about admission controller integration. That's the second way to integrate into Kubernetes. Also, for those who don't know, an admission controller is a plugin system that was introduced in Kubernetes 1.25, or it was considered stable with 1.25. And it allows to write plugins that let you intercept API calls in Kubernetes and either validate them or modify them. And Sigstore actually provides its own admission controller. It's called the policy controller. We can also define policies to actually put requirements on the download of images. Just as a little caveat, it's still under development, so it's not considered production ready yet. Okay. Yeah, so how do you actually configure that? The policy controller introduces a new object. It's called cluster image policy, with which you can define your policies. And to actually enable it, since it's namespace based, you have to enable it on with a label in your namespace. In this case, policy.sigstore.dev/include equals true. And again, I have brought you a little example for a cluster image policy. There we have two important parts. One being the image. In our case, we just say we want to apply the policy to all images and authorities. With authorities, you define what system you want to use, because Sigstore supports some more systems I haven't shown you due to scope. In our case, it's keyless. That's the one I have just showed you. And there we give the necessary information again, here being the full queue URL with the certificate as a secret. And in this case, we give two identities. So when the image is checked, either one has to be true, or one has to be true. And a little special thing here is there's an example for how you can do that with GitHub Actions. That's a pretty neat thing, because GitHub Actions actually allows you to create, or automatically creates a token for you in the action, so you can just use the variable. And there's another neat thing that is usually not talked about, or not that profoundly. If you have a certificate and you have your subject ID, since you use your own account, your personal or work email address will be used for the certificate. And then the certificate will be uploaded into an append-only log that is public to everybody. And maybe you don't want to be associated with your account or with the image you have created at some point in the future. And this is currently one of the ways you can actually don't use your email address. And instead, if you use GitHub Actions, it will use the path or the URL of the actual workflow. Yeah, I have been much too fast. Funnily though, I stripped half of the talk because I thought I would be too slow. So I can just talk to you about two neat features that Sigstore actually has, and they are called attestations. Attestations are the concept where you, so what Sigstore currently does is, it takes your image, puts it in a registry, puts the signature next to it, done. But then they thought, hey, we have a registry that can have arbitrary artifacts, and we have a system that can create signatures, so why don't attach data to it? So we could just go and say, all right, what about an SBOM? So we have a software bill of materials that actually contains all the dependencies our image have. When we create the image, we create the SBOM, we create the signature for it, we upload it to the together with the artifact into the registry. It will be signed the whole same way. And now we can start something that is pretty interesting, because what we can do now is we can use this forwarding of trust through proof. Like, we have the trust into the root, and this trust is through proof deployed in the whole network, in the infrastructure parts, and by extension into the signatures. And now we can use that to actually not only ensure the authenticity and the integrity of the image, but we can include proofs over other properties of our image. So if I have a security audit, I can add the security audit as a proof. There's something called in toto attestations. Do anybody of you know about that? No? Okay. In toto attestations are a metadata format, which actually lets you, in a formal way, include some properties of your software. For example, in toto supports that you can show via a third party, in this case GitHub, that a test in your CI was successful. And now you have a toto attestation that attestates you over a trusted third party, and at this point GitHub, that some property of your image is true. You can attach it to the image and then sign it and upload it. So this is, yeah, great stuff. Okay, conclusion. All right, conclusion. I hopefully have shown you that Sigstore as a system allows you to authenticate and ensure the integrity of packages in a way that is compliant with modern package management systems by circumventing the whole scaling problem. They circumvent it by introducing themselves as a third party. And by that, you'd only need to trust one party, or depending on if you set up your own Sigstore, the other Sigstore party, making it more manageable. And then I want to end on some caveats. So Sigstore solves a very specific problem. And the problem with such solutions is usually if you don't have good security practices and transparency processes, it doesn't bring you anything. Because what we did with Sigstore is, for example, we exchanged our private key we can lose with credentials to an OIDC provider we can lose. So if we don't take care of our credentials to our OIDC provider, then we don't have gained anything. And the other point being, Sigstore is a complex system, a pretty complex system. So what we did again is, we had a lot of complexity. We took a little more complexity and used it as a bandage to put it on our complexity. And that is the reason why you should all the time consider if you are really, if it is really necessary to use that kind of complexity in your system, or if you can work without it. But in the end, Sigstore solves this problem quite interestingly, and I think it's a good cornerstone to build upon. Yeah. Thank you. Yeah, that's my contact data. That's the QR code to the slides. And now we have an extended Q&A, if you like.